Collision theory. Now, we did look at collision theory briefly in the last video. Remember, the last video was activation energy and potential energy. So if you're not very competent with this topic, I highly recommend and suggest you watch this video first prior to this video on collision theory. But the previous video, warping around these topics, was how a reaction can proceed, the two different metrics that are required. Well, the first metric for the reactants, right, the particles of the reactants that are about to undergo a reaction, in order for that reaction to proceed, the first one was about the geometry, right, the correct geometry orientation between the particles and the reactant particles. And then the second was a sufficient amount of energy, so sufficient energy, okay, kinetic energy, that is required in order to either hit the activation energy threshold or be greater than that activation energy barrier threshold. As long as both of these are suffice in being hit, that reaction will proceed and the products will form. However, right now, we are just going to look at the different factors that affect the reaction rate. So I'm just right here on the side. What factors affect the reaction rate? Okay. Well, the first one, we'll just do it in a numbered list, is going to be reactivity. Okay? And what does this mean? Well, here I'll give you an example. I'll give you an example. First one is for more bonds. If there are more bonds, this means that there is going to be a slower rate of reaction. Now, let's have a look at this one with 5C2O4. And it's an ion here, added with 2MnO4, also an anion, and then we're also going to add 16 hydrogens. This is a cation, and this is all going to be producing 10CO2 plus 2Mn, 2 plus, and 8H2O. Now, I want you to look at this equation and compare it. So versus Fe 2 plus and Ce 4 plus, Fe 3 plus, and Ce 3 plus. Now, we have to look at the one that has more bonds. Of course, this one here has a lot more bonds because we see that the bonds are forming on this opposite side, whereas over here, the bonds are not forming. And not only do we have to look at the amount of bonds that are forming, but also if they are stronger bonds, okay? If there are stronger bonds, this also has a slower rate of reaction. So I'll just put it here on the side as a footnote, okay? Stronger bonds also is equal to a slower rate, okay, of reaction. That's number one. Let's look at number two. We have ionization energy. Okay, you should be familiar with ionization energy. If not, please look at my previous video from a while ago about ionization energy and electron affinity. It's important. So when we have an ionization energy, let's have an example again, in brackets here, of high ionization energy. Okay, and if it is low in electron affinity, what do you think this would happen? Would it be a slow rate of reaction, or would it be a fast rate of reaction? Well, let's give an example over here. I'm going to show you neon, so right here, neon. Okay, and obviously neon is a noble gas. Okay, let's draw it out. 1s, it's going to be completely filled, obviously, and then we have our 2s, obviously completely filled, and our 2p, in and around the same level, okay, is also going to be completely filled. Okay, well, we all know that the ionization energy is the total amount of energy that is required to remove the outermost electron from the valence shell. So if this one electron here, doesn't matter which one, let's say it's this one, okay? Is it going to be easy to take off this electron? No. The answer is no. It's going to be very difficult because it's already very stable here. So this means that this is high ionization energy, okay? Because the amount of energy to be absorbed to take off the electron would have to be an enormous amount in order for that electron to be removed. How about the electron affinity, okay? Which is effectively the amount of energy that it will give away in order to take an electron. It definitely doesn't want to take an electron, so it's not going to give away any energy. So this would be a low electron affinity. It's not going to give away money in the form of energy in this case, okay? It's not going to give off any money in order to take an electron. It doesn't need it. It's already very happy. So in this case, it has a very high ionization energy and a very low electron affinity. So in this case, obviously, this is going to be a lower rate, okay? It's going to be very slow. Therefore, slow. Okay, so that's what we have here. So then obviously, therefore, okay, it's going to be the opposite for an ionization energy if it has a low ionization energy and a high electron affinity. So this is going to be the opposite, right? So therefore this will be a fast, okay, rate of reaction. The third one here is going to be temperature, and this one should be quite obvious by now. For temperature, an example, if there is an increased amount of it, what do you think is going to happen with the rate of reaction? Of course, it's going to increase the rate of reaction. Okay, why? I mean, it should be quite obvious, but due to the increase in kinetic energy, right, of all particles, okay, this is going to equal an increase in the amount of collisions. What does that mean? If there is more collisions occurring, there could be an effective amount of collisions that can overseed the activation energy barrier, or even just hit it right at the threshold, which would still be able to overcome that barrier. So regardless, the amount of collisions, okay, whether it's going to be effective and not effective, it's just going to increase the probability. So if there is still an increased amount of collisions, there could be a lot of non-effective ones and there could be a lot of effective ones. Regardless, you are increasing the chances of the effective ones. So this is going to increase the effective collisions too. So therefore, it's going to increase the rate of reaction. Next, so that was number 3. Now let's look at number 4. Number 4 would be concentration. Okay, but the concentration is kind of similar. For an example, if we increase our concentration, what's going to happen? Well, this is also going to increase the rate. It's very similar to what we saw above. I also want to put a note here. How can we increase this concentration? Well, the first one, I'll just put it as I. Okay, the first one that we can do is evaporate the solvent. And this should be quite obvious. If you were to have a glass of water and then there's, a lot of solute within that solvent, okay, within this water layer, okay, as if you get rid of all this water, what have you have left? All these dots over here, those dots are the solute, like salt, for example. So of course, when you get rid of all that water, it's going to be less dilute, and therefore it's going to be evaporated, hence a higher concentration. All right, so that's one way. Another way could be adding more reactant. And this is just by adding more of, those salts, for example. So that's adding reactant. And another one could be increasing the partial pressure. Increasing PP, the partial pressure. Okay, how do we do this? Well, we can just compress it. So if we had a way up here and then was able to bring this all the way down, okay? So we, instead of the line being here, whatever that is, the cap, and it's all the way down here, for example, all of the solutes, or the gases, for example, because we're talking about partial pressure, okay, the gases here would be compressed in this tiny little space of volume, and therefore this would increase the amount of pressure, because we know that between those two variables, they are inversely proportional. Let's look at our fifth factor. We just increase surface area. Okay? Here, I'll just put it here, surface area. So, if we increase surface area, this is also going to increase the rate of reaction. Now, how do we know this? It's because more particles are exposed. Since more particles are exposed to collide in the same amount of time, and let's have a look at an example of that. So, for example, let's look at wood shavings, and we compare that with a wood block. Which one's going to be easier to burn? Of course, the wood shavings. Okay, this is going to be quite obvious because there's an increased amount of exposure for those reactant particles to burn. It'll be easier to react. Whereas with the wood block, they're all kind of compact within one another. There's less surface area. There's going to be more volume, but less surface area. So it's going to be a lot more difficult for a lot of reactions, a lot of collisions to happen at the same time with the ignition of the fire. Another example would be a sugar cube in water. Of course, it's going to be a lot more difficult for a whole sugar cube to dissolve within the water as opposed to having a lot of different sugar particles here just thrown in that same amount of water. Okay, so obviously if you have a cube here, a sugar cube, okay, obviously here it's going to be a lot more difficult for the collisions to happen in the same amount of time as opposed to a sugar that is just powdered and just thrown in. Okay, so then let's have a look at the sixth one. The last one is going to be a catalyst. So we just add catalyst. Okay, adding a catalyst will also increase the rate of reaction. Okay, increase the rate by decreasing the activation energy, or the energy of activation. Therefore, there will be more effective collisions. So I'd like you to see the previous video where I go into detail about a graph and talking about the activated complex here, because I go into detail about how a catalyst decreases the level of the activated complex in regards to the potential energy of the graph, so that it's easier for the collisions that are effective to hit that activated complex for that reaction to proceed. So please look at that previous video to go more into detail with that. But regardless, let's have a look at this increased rate. We have an increased rate because we're going to have more products being formed due to this decreased activation energy. And therefore, rather than hitting the activated complex over there, we're going to be hitting the activated complex here. Also, catalysts also improves the molecular geometry of collision. Also improves the molecular geometry. Okay, for the particles to be oriented with one another and successfully hit at that particular angle, at that particular area, provided that there's also a sufficient amount of energy so that the products can be formed easier so that the reaction can proceed. Let's look at this example. The enthalpy change for the conversion of graphite to diamond is plus 1.9 kilojoules per mole. As you can see, it's not a lot of energy. And you can tell that this is going to be an endothermic reaction because we're going to have more potential energy than we had in the beginning. So this small energy difference suggests this conversion is very simple. What information is not shown by the equation that would help explain why this conversion is not a simple process? I mean, obviously, we can see here graphite. I think we all know graphite is within our pencils, right? The ones that we use in school all the time. Of course, for that to become a diamond would require what? Everyone should know this, right? Diamond requires a lot of pressure and a lot of temperature. So how come this plus 1.9 kilojoules is all that is needed for this diamond to form? What are we missing? That's what the question is asking for. What are we missing? What we are missing is the activation energy. Okay, what is the activation energy for that? Of course, the activation energy would have to be extremely high. So if we had a graph over here, okay, and this is our little PE, okay, and this here is our reactant, our graphite, it's going to be a very, 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 very high activated complex, okay? So the activation energy is going to be very, very difficult, okay? And as you can see, it's only plus 1.9 kilojoules. So in terms of where it's going to be, it might be over like here, okay? But in order for this product to be made, right, this here is the diamond, okay, and this here is our graphite. This range between our reactant over here and our product over here is very, very small, okay? It's only 1.9 kilojoules. But in order for that reaction to happen, this huge amount of activation energy would have had to been required, okay, to hit that activation energy barrier threshold, this whole thing up here, and hit or be greater than this activated complex up here in order for that reaction to proceed. So it was a lot of work. It's very difficult. But the enthalpy at the very end here is very small. It's only 1.9 kilojoules. Okay, but within this equation here, it doesn't say anything about this activation energy. It looks very easy, looks very simple, not that difficult. Okay, but the process in order for that to occur, as you can see, is a monumental step. Okay, let's look at this next question. Given the data for a reaction, activation energy forward is equal to 45 kilojoules and activation in the reverse direction is 50 kilojoules. Is the reaction endothermic or exothermic? Well, let's draw this out first on this little graph here, okay? Again, that's going to be PA, and then this here is going to be the reaction progress, okay? I'm going to the right side, okay? So if we have 45 kilojoules, so let's just draw our reactants, okay? If we have 45 kilojoules, so I'm just going to arbitrarily put, an activated complex over here, okay? And it's going to be 45 kilojoules, so this here would be in the forward direction because we're starting with the reactants, we're going in this direction, so obviously this here would be the forward direction, okay? We're referencing the reactants, so this is going to be 45 kilojoules. I'm just going to write this here, 45 kilojoules, okay? But if we do it to the reverse reaction, this means we are now referencing this activated complex with the reverse, okay, which would be the reference to the products. Again, see my previous video on activation energy and potential energy when I talked about this activated complex, okay? So if we go down, okay, we've hit 45, but this is not where our product is at. Our product is going to be a little bit lower because we need to hit not 45 but 50. So this kind of looks like 50, okay? So now this is like 50 kilojoules, okay? So hence our product is going to be like here. Oops, that's going to be a little bit straighter. Okay, this is going to be our product here. Okay, so you can see the difference. This is a little bit longer, and because the products are over here, this is going to be in the reverse direction because we can't start on the product side because we're not going right to left. We're going the opposite direction. We're going left to right. So therefore, this would be the reverse reaction. So if we look at the difference between these two, so between this reaction and between this product here, what is the difference in between? Okay, this here is going to be 5 kilojoules. Okay, so what is the magnitude of delta HR? Well, it's going to be 5 kilojoules, but remember, this is a difference of 5. However, because we have our products here that are lower in potential energy than our reactants, this means that this is an exothermic reaction. Why is this the case? Well, if we have our activation energy, okay, and if it's our forward one, if the forward one is less than the activation energy of our reverse direction, this is going to be exothermic. It's going to be a negative value because we are losing energy. Okay, we had a certain amount of mass here, we have a certain amount of mass here. Okay, where did the energy, this leftover 5 kilojoules, go? It got released as energy. It can't just disappear. Okay, it can't just disappear. It got released. Okay, so that energy got released in the form of 5 kilojoules. Okay, because the reverse is going to be greater than the forward. Hence, it's going to be a negative value of negative 5 kilojoules. That is the answer. Oh, and again, this is exothermic. So that's the answer. Well, let's look at this question here. Use collision theory to explain the effect of a decrease in temperature on the reaction below. So obviously a decrease in temperature is going to decrease the amount of kinetic energy, right? So it's going to decrease kinetic energy, okay, of the particles, of the reactant particles. And if there's going to be a decrease of this reactant particles of the energy, there's going to be less kinetic energy transferred to the neighboring particles. Okay, so if there is less energy transferred to its neighboring particles, then the whole thing, right, the thermal energy and the whole thing, right, the addition and the sum of all the kinetic energy of all the particles put together is going to be overall a lot smaller. So this means that there is going to be therefore less products made in that same amount of time. And if there's less products made in that amount of time, so let's look at our little graph here. Okay, so let's say this is our activated complex. If you don't have a lot of energy here, okay, of the kinetic energy like I've mentioned here, or it being transferred to its neighboring particles, these reactants won't be excited enough to hit this activated complex. And if there's less of them hitting this, there's going to be less of these products being formed in that specific amount of time. Now, it's not going to change the delta H, okay? So this difference between the reactant and the product over here, okay, that delta H is still going to be the same. That's not going to change, but the amount of time that it takes for this release of energy, because every time we go from these reactions to become products, there's going to be a release in this amount of energy, since these products have a lower potential energy, right, has a lower potential energy than the reactants, right? It's going to be more slow, okay, because there's less of these reactant particles that are able to hit that, because we've put a decrease in temperature. Okay, if we have a decrease in temperature, there's less effective collisions that are going to be hitting here, regardless if they have the right amount of geometrical orientation. If they don't have sufficient amount of energy to clear this threshold, this barrier, then it's not going to work. And we're going to have less products being formed, which means there's going to be less amount of energy being released in that same amount of time. Let's go to this last question here. Iron will rust as shown below. Use the equation and collision theory. Explain how the rate at which the rusting could be slowed down. Okay, well, we know that rate of reaction depends on these 6 things that we looked at. Okay, so obviously if we decrease the temperature, okay, this is obviously going to decrease the reaction rate. If we decrease the amount of surface area, so if we were to cover a certain area of this iron so that it doesn't react so much with the oxygen, right, because obviously oxygen is in the air. It's about 20% of the air that we breathe and that we're always moving within, okay, throughout our everyday life. If we were to cover it, okay, with something, then obviously less of that iron is going to be reacting with that oxygen every single second. So we can just decrease the surface area. That's going to obviously decrease the rate at which the rusting occurs. Now, this here are our 2 green questions of the day. Please pause the video, give this a try, and I'll be giving the answers shortly. Oh, sorry, before I give you an opportunity to look at the answers. For this question over here, right, we have a 2 centimeter cube of aluminum, in case you kind of need a refresher on the surface area. If we have this cube over here and this cube, okay, and I know it says, what is it, a 2 centimeter cube, right? So obviously for a cube, this side here has to be the same as this side. So if this is 2 centimeters, obviously this here is also going to be 2 centimeters, okay? So if you just multiply them together, right, so you just get that, okay, you're just going to get 4 okay, centimeters squared. So what's going to happen? Well, this 4 centimeters is just on what side? It's just in the area for this side over here, okay? However, in a cube, how many sides are there? Okay, we have this side, the front side, but we also have the back side over there, and then you also got the top side up there, and then you got also got the right side, and then you also got the left side, and you even got the bottom side over there. There are 6 sides, right? So instead of 4 centimeters squared, if you multiply by 6, what do you get? 6 times 4 equals 24. Okay, so this here is your surface area. Hopefully this helps. This is the answer to the first question. This here's the answer for the second question.